Yeah, the class average is 60.
It brought me down.
Okay.
Why wasn't as smart as you?
All right, so when we are talking about materials, you know that certain materials heat up faster and cool off faster than other materials out there. For example, if you have just a pot on your stove and you heat that up, it's going to heat up very quickly. And then if you turn it off and set it off to the side, it's going to cool down very quickly. As opposed to the water inside that pot, it's going to take longer for that to heat up and then longer for that to cool down as well. The difference between these things is called heat capacity, specific heat capacity. So each material out there has a different specific heat capacity. That's why when you take like a baked potato out of the oven that's been in there for a couple hours baking, right? You open the foil, you can actually take your fingers and open that foil up and not get burned, right? After it's set out for a minute or so, because that foil cools off very quickly. But the potato inside there will burn you because it's still very hot. The potato has a higher specific heat value than that aluminum foil, okay? So the tendency of things to heat or cool and how much heat that they can hold varies by the material. That make sense? Well, the metal gets a little funky.
It burns.
No, the metal will actually conduct the like it ends up sparking. It gets yeah.
Plastic, no. You put plastic in the microwave, doesn't that melt? That home starts on fire.
You guys ever want to do something fun? Take a bunch of empty
All right.
wrappers and put them in the microwave.
So far.
So the
Or chip bags.
heat is Q.
Why is he Q? Why is it H?
Okay, so heat is Q. The mass of the object is M. The specific heat value is a capital C. Where's my pen? Is my pen not working now? It's not. There we go. Is C, and then the change in temperature is your final temp minus your initial temp. This delta sign here, this triangle, means change in. Okay, so we're going to be looking at a specific heat capacity. The specific heat capacity is the amount of energy needed to raise 1 gram of a substance by 1 degree Celsius. And here you have to have your temperature in Celsius. Each substance has its own specific heat capacity. For example, this is the one for water. Its label is a capital C and its units are joules per grams degrees Celsius, or in some cases you will see Kelvin, but traditionally in AP they have this in the Celsius variety. You need to be careful when you're given your specific heat capacity to look and see what they have your temperature in. If your temperature is given in something different, then you need to change your temperature to match what your specific heat capacity is given in. Does that make sense? Or else your units aren't going to cancel properly. But I have not seen or noticed that I can recall an AP problem where the specific heat was given in Kelvin here instead of degrees Celsius. Okay. All right, so heat is a form of energy. It's going to flow between two samples. We talked about that yesterday. We talked about the 3 different ways that heat can move. And it's always heat that moves and not cold. Okay. So heat is going to transfer from something that's hotter to something that is colder. 1 joule equals, this is 1 calorie. Let me see, is that on your sheet? Do not see that on here.
Is the equation on our sheet?
Yeah, the specific heat equations on your sheet. If you look at your sheet here, it's thermodynamics here, is this bottom quadrant, and it's the first equation on there. Okay, so this equation is given on that sheet right there.
Is this format of this fact sheet how the
Yep. Except this will be 2 pages, and here I've put it on 1 to make it more convenient for you. But you'll have this on 1 page. This is the second page, and this will be the 3rd page. Yeah. But I thought that it would be more convenient to have it on 1 sheet than to try to keep track of 2 different sheets like this. So that's why I printed it like this for you. All right. So they give you that. You've got 1,000 calories is 1 calorie with a capital C. 1,000 calories equals 1 kilocalorie with a lowercase c, and 1,000 joules is going to equal 1 kilojoule. So these are just kind of helpful things to kind of remember about the metric system. Most textbooks use a lowercase c or an uppercase c for specific heat. And others, you'll see it as an S, but that's pretty rare. You might see that in college, but I kind of doubt it. All right. Calorimeter then is a device that you're able to kind of measure the heat that's transferred. When you did this, if you had me for pre-AP previously, you would have most likely done a lab where we had metals. We put them in a styrofoam cup, and then we measured the temperature difference. Those styrofoam cups actually work pretty well for this. So what you do is you put water in there, you measure the temperature of the water, then you put your hot metal in there, measure the temperature that the water changes to, and then you're able to figure out what the specific heat of the unknown metal is. So we know that when we do this, that the heat of the metal is going to equal the heat gained by the water. And so we can use this, we can rearrange this where we have the metal times the specific heat of the metal times the change in temperature equals, and this is going to be negative over here, negative water mass times the specific heat of water times the delta T of the water. Now this is going to increase in temperature, and this will decrease in temperature. So this will be a negative value, which cancels out this negative sign here once you divide it out. All right. So here, each substance, like I said, has its own specific heat capacity. So if you compare aluminum and lead here, the specific heat of aluminum is 0.9 joules per grams degrees Celsius. Specific heat of lead is 0.160. So that means that the lead is going to cool off faster than the aluminum. Okay, adding heat into here, into the aluminum, it's going to not go up as high as the lead. It's going to take more heat to get this temperature raised up of the aluminum than it would the lead, because you have to pump more in to get that to raise. Heating a system then results in the system having a greater energy because the energy is going into the system, while cooling the system causes it to have less energy leaving the system. Specific heat capacity then is measured as an amount of energy needed to raise 1 gram of the substance 1 degree Celsius. Molar heat capacity then is the specific heat divided by the molar mass of the substance, and it's measured as the amount of energy needed to raise 1 mole of the substance 1 degree Celsius. You may be provided with either, so you always want to kind of check your problem units to make sure that they haven't snuck in that mole in there. Okay. Also remember that with these heating and cooling curves, when we are looking at these, that during a phase change, what do we notice? Temperature does not change. Okay. What is happening to the substance during those transitions? Right. If we're going this direction, your IMFs are being weakened or broken. If you're going this direction, then they're being reformed or strengthened. Okay. Chemical systems change their energies through three main processes: heating and cooling transitions. So you can use this formula to figure out any time in this transition, or this transition. Why doesn't that formula work here and here?
Multiply by 0.
Right, your temperature is not changing, so therefore that formula will not work for you. We're going to look and see what we're going to do during those phase transitions in just another minute or two. Okay, so we have to use something different to calculate the heat that's being applied there. All right, so here we've got almonds and cashews. They're being burned at a bomb calorimeter, which is a fancy calorimeter, not like our styrofoam cups. They're containing water, and they gained this data here. They want to calculate the energy for each nut, which one will provide more energy per gram. Okay? So, first thing we need to do is we need to set up our equation. We're going to have two different setups here because we've got two different nuts that we're working with. So for the first nut, we've got our water here. And we know that our mass of our water, they didn't give us mass, they gave us volume here. They gave it in milliliters. They said mass, but they gave us milliliters, but we know what?
It could be in liters.
No. What do we know about water?
That's 22.4.
No. No.
It evaporates.
No.
Equal to.
What's the connection between the mass and volume for water?
It's the same.
Why?
Because
Because the liquid always forms.
No.
Because the metric system is based on.
No.
because it's equally distributed.
No.
Water is measured in milliliters. Water is measured by the because it's almost Valentine's Day.
Mass over volume.
Density. Yes.
Density of water is 1.
Density of water is 1. So if we know the density of water is 1, we know that this is going to be 2,000 grams, and this is going to be 1,000 grams.
Oh my goodness.
So the formula for density, remember, is love. Mass over volume.
Oh, I was wondering why there was a heart up there. That's why I got it.
Mass
Wait, when did you write
over
that?
volume.
Remember, she used to write down.
Jaden said because it's Valentine's.
No, I said that because she was like drawing a heart. I was like,
Remember, that's how she knows.
I've never
She's
seen
like, remember, density.
Mass over volume, which happens a lot on Valentine's Day. Okay, so we know this. If we can calculate the heat gained by the water, that's going to tell us the heat lost by the nut. Okay, so if we know that this is 2,000 grams, right, times our specific heat of water is 4.18 joules per gram degree Celsius. And then we need to figure out the change in temperature here. What is the change in temperature here?
18.
What? Ellie? Yeah.
Why is that so shocking that I was able to do that like that? Well, smart.
You want us to be honest?
Excuse me? Matthew didn't know how to do that. Matthew said, what?
So you calculate this out. What do you get? You actually have a calculator as opposed to me.
Let me get my calculator out. This one we got, no worries. 2,000 times.
8,000 something
Oh.
joules.
Come on, oh my goodness. Hold on.
Yeah, I could be on the net.
150,480. I did that all in my head, by the way.
Oh, we have to test about 18.
What's the RJ?
Kilojoule.
Retro.
Because it's in joules, right? But you made kilojoules, so you have to write
146.
Duh. Come on, Matthew. I should have made
Okay,
my mind.
so I did this for almonds. You figure out what cashews are.
Okay.
Okay, we can do this, Libby.
1,000.
You don't have to say it out loud, Al.
I'll do what I want. $120. No. For the temperature. This is not the answer. What? 28 is the temperature.
No, I'm not. Oh, yeah.
All right, did you get 120 kilojoules?
Yes, you did.
Do you have
Okay.
to?
Now they want to know per gram. Okay. So when we say per, what operation do you do mathematically? Divide. So we're going to divide by the grams of each nut to get that value.
No, I see.
Why do we divide by grams?
Because they wanted to know, calculate the energy for each nut, which provides more energy per gram.
Did everyone get equal? No.
So 150 and 120
I got
would be the whole
24
nut.
and 25.
I got 25.
And then 25 and 24 would be for just the grams.
We don't have to. I'll take it 24. It's okay now.
150 is so almonds.
Yes, almonds are going to give you more energy.
Well, that's a 5. There was a 6 up there. And it was under 20. Sorry.
Unacceptable, Matthew.
That's why it's 24. All right. Makes sense.
All right.
Almonds are the superior nut.
So the next one here, we have 8 hydrochloric acid. It's getting added to NaOH. We have the initial temperature. This is the reaction we're going through. We've got the final temperature here, which is 26.3. They want to know the heat gained by the mixture. Okay. You're going to assume that since this is mostly, all of these are aqueous, that the majority of this is water. So therefore you can use its specific heat value to be able to calculate your answers here. So Q is going to equal the mass of our reactants. So what is the mass of my reactants?
5.
Wait, what's the equation?
Molarity equals mass over volume. So you do.
No, that's density.
No, it's
No. Isn't it mass over volume?
Oh, no, I was able to the number of moles divided by. So you do 50 times 0.5. Right?
Equals mass over liter.
So what is my mass of my liquid here?
25.
100.
25
You've got 50 mils of this guy
Oh, I didn't say 0.025.
and 50 mils of this guy. So that's 100 grams times the specific heat of water.
4.1.
And what temperature change did we have? We went from this
6.5.
to this, 6.5. All right, my Celsius is going to cancel, my grams cancel, and that's going to leave me with joules, which makes sense for energy. So I multiply that through, I end up with 2719.6 joules. Okay. So that is the first part of that question. Any issues, questions, or problems? Anything? Anybody got lost in the process?
Sig figs. Which you'll need.
Sig figs, yeah, sig figs are an issue here. You're right. So I need 3 sig figs, it looks like. So that would be 2720 joules. Better?
Yep.
Yeah.
Okay.
Wait, so 2719 is the heat for like the joules.
Wait. Polarity is
Oh, that's not.
Oh, we didn't even use that.
Oh, wow.
I thought that was is that 6.5 or 6J?
But there's no water, so
6J joules.
Oh.
why?
Because it's aqueous, yes.
So that's why we don't have to use the molarity.
So all H.
If it's aqueous, you can assume it's mostly. You can just assume that that's going to be somewhat close to water.
Does dissolving something in water make it gain mass? It does, right?
The density will-
Yeah, a little bit.
That's a wish. Ellie, do you want me to change your calculator over?
Yes, wait, how do you do that? What does that even do? What does it do?
All right. Then they want to know the heat of reaction per mole of NaOH. Okay. So here we have, here we're going to have to calculate the number of moles of this. So figure out your moles. Molarity equals moles over liters.
You have to add the two of each. because-
No, they're asking specifically about this.
So it's 25 moles.
No,
No, it's not.
0.025.
Yes. Okay, your molarity is 0.5. Your moles are what you're solving for, and this it has to be in liters. So this is 0.050 liters. So that means that your mole value is going to end up being 0.025 moles. So if they're asking the heat of reaction per mole, that would be 2720 joules per 0.025 moles equals So I had 108.784 joules per mole. And if we want to get into sig figs, it would be 109 kilojoules per mole.
Did you carry over the 2720 from above?
Probably.
If you don't, you get 18.
Yeah, I would have probably had the 2719.6 here. divided by that. I keep all my digits in my calculator. I don't clear out. I try to keep it going forward. And for the AP test, as long as you show your work, that's all that matters. They'll take care of you. Okay. All right. So that takes care of that takes care of during our heating and cooling. We need to talk about during phase changes. So during phase changes, you're going to have heat released or absorbed. And during those phase changes, the temperature doesn't change. So during that process, we can't use the same equation because during these phase changes, temperature doesn't change. So we have to look at values here that are called heat of fusion. Okay, they call this heat of fusion. It's like your specific heat, but it relates to this. And this is called heat of vaporization. And you can keep that kind of straight in your head because when you're taking this, you're taking liquid molecules and kind of fusing them together to make into a solid. And then here you're vaporizing them. You're changing it into a gas. So that's kind of the way I keep track of it in my brain, the difference between the two. Okay. So you're going to calculate the heat needed to perform a phase change when we have this. You're going to multiply the mass times that delta H or the heat. And then your mass is going to be in either mass or in moles. And then you'll have the enthalpy of change, heat of blank, or the molar heat of blank. So heat of fusion, heat of vaporization. All right. So these are called, melting is called freezing. So if we go this direction, it's called freezing or fusion or crystallization. This way is called melting. Here we're either boiling or vaporizing. And then here we're going to be condensing. So when we look at these, we've got heat of fusion here given for mercury. We've got its melting point. And then we have heat of vaporization for mercury. And then we've got its boiling point as well. So given this heating curve for mercury, calculate the heat needed to freeze 100 grams of mercury at its melting point. Okay. So Q is going to equal the mass times the delta heat of fusion. So Q is going to equal, in this case, it's going to be 100 grams times that heat of fusion here, which is in kilojoules per mole. Hold on. I'll write that down. Okay. I'll get it right this time. All right. The problem is what? Moles and grams. But we can do what? Right, we can change mercury. We can get the value off the periodic table and change that out. So if I do that, that gram value is going to go down in the bottom per 1 mole of Hg. This is coming directly off of my periodic table. So mercury on my periodic table is, can't even read that one, 200? 200.59, so 200.6. So 200.6 in every 1 mole. So now my moles are going to cancel, my grams will cancel, and that's going to leave me with kilojoules. So Q is going to equal 1.147 kilojoules.
Why do you have to change it into moles or grams?
Because they gave it to me in grams. This value was given to me in kilojoules per mole.
So technically, do we have this in the actual equation, or can we do that before?
Yeah, you could do it before. That's fine. Now, this is freezing. So what do we know about the energy here? It's going to be negative because we're losing energy here. Okay? It's exothermic. Yep.
That's just reading the equation you have to read.
Yep. All right, good. Questions? Make sense? All right, let's look at the we do real quick before the bell rings. We've got aluminum. It's going to melt or freeze at 933 Kelvin. How much energy is required to freeze? That means energy is going to be doing what? Negative. It's going to be exiting. 2.5 moles of aluminum at 933 Kelvin. Here is your fusion and your vaporization. Which one are we going to use here? The first one or the second one? This guy right here. Okay. They've already got this into moles for us, which is nice. Moles. I'm going to get rid of my moles. So this is going to be 10.9 kilojoules per 1 mole on the bottom. And when we calculate that out, and remember this is losing energy, so we need a negative here. Negative is going to be our answer. And that's going to be 27.3 kilojoules. All right, good?
Yeah. We're driving, looking.
All right. So tonight is 6-4 and 6-5.